A boost regulator is a DC-DC converter whose output voltage is always greater than the input voltage. It uses a switching element to regulate steady DC output of required voltage. I am Reshma, and today we will discuss the operation of a boost regulator in continuous mode of operation. In this video today, we will see how we can use the equations of previous videos to arrive at a starting point for designing a boost regulator. We will discuss on the following topics: inductor design value, inductor design of average and peak currents, inductor design of losses, switch and diode design. Let us try to design a boost regulator in continuous conduction mode. Let the required output be 15 volt and maximum load current be 1 amps. Let the input vary from 5 volt to 12 volt. Let the inductor ripple current maximum be 30% of inductor maximum current. Let us switch it at 100 kHz. It is to be noted that we are dealing with continuous conduction mode of operation. Since the values are theoretical, they give a starting point. However, they need to be validated in actual hardware. Based on these actual hardware measurements, some changes may be required in the design. We know that time is inverse of frequency. Hence, total time period is given as 1 by switching frequency, that is equal to 10 microseconds. Now, let us calculate minimum and maximum duty cycles. We know that duty cycle is given as 1 minus V in divided by V out. D minimum occurs at maximum input voltage. Hence, on substituting these values, we get D minimum as 1 minus 12 volt by 15 volt, that is equal to 0.2. Similarly, D max occurs at minimum input voltage. On substituting the minimum values in this equation, we get 1 minus 5 volt by 15 volt, that is equal to 0.66. Let us now calculate the input current at low line and high line voltages. Maximum input current occurs at minimum input voltage. Let us now substitute maximum duty cycle value occurring at minimum input voltage. It is given as 1 amps divided by 1 minus 0.66. This is equal to 3 amps. Minimum input current occurs at maximum input voltage. Let us now substitute minimum duty cycle. This occurs at maximum input voltage. That is given as 1 amps divided by 1 minus 0.2. That gives us 1.25 amps. The inductor ripple current can be calculated as 3 amps into 30%, that is equal to 0.9 amps. Let us now calculate the inductor value when input voltage is 12 volt. Duty cycle is minimum when input voltage is maximum. Therefore, D minimum is given as 0.2. We have seen earlier the change in inductor current during switch turn on is given as DIL on is equal to V in into D into T total divided by L. On substituting the known values, we get L is equal to 26.6 microhenry. Let us now calculate the inductor value when input voltage is 5 volt. Duty cycle is maximum when input voltage is minimum. Thus, D max is equal to 0.66. We have seen earlier the change in inductor current during switch turn on is given as DIL on is equal to Vn into D into T total divided by L. Let us now substitute these values to get L as 37 microhenry. If we notice here, we have two values for inductor. Which one should we use for design? We have to choose an inductor value of higher inductance. This is because if we use an inductor with smaller value, then at high line input voltage, we will have a ripple current of more than 30% in the inductor. Thus, L is equal to 37 microhenry. Let us now calculate the inductor average current. The average inductor current is the input current. We have calculated earlier the inductor average current at low line as 3 amps and at high line as 1.25 amps. We know the output load current is equal to 1 amps. We have seen earlier that inductor peak current is given as shown here. Substituting the known values, we get the equation as shown. As we have two duty cycles, one with low input voltage and one with high input voltage, let us calculate inductor peak current value for those two values. So, at 5 volt input, duty cycle is 0.66. With this value, we get 3.45 amps. So, at 12 volt input, duty cycle is 0.2. With this value, we get 1.57 amps as peak inductor current. Here, we need to select high peak inductor current value while selecting the inductor. We have seen in our previous videos that DC loss of the inductor is given as R inductor DC into I1 square plus I2 square plus I1 I2 divided by 3. This is also equal to R inductor DC into inductor average current square plus ripple current square divided by 12. We need to calculate the inductor loss at maximum current. Thus, on substituting these known values, we get the following equation. On simplifying, we get inductor average power is equal to R inductor DC into 9.0675. Here, we do not know the value of R inductor DC. This can be found from inductor datasheet or it can be measured using suitable instrument. Let us now look at switch design. The switch voltage is given as output voltage plus diode voltage. With this, we get switch voltage as 15.7 volt. However, in practice, the switch must be rated at least 30% more than this voltage. This will lead to 20 volt. Let us now look at switch current. Switch average current is given as D into inductor average current. We consider maximum duty cycle which occurs at minimum input voltage. This is when we have maximum switch current. Let us substitute these values in switch average current equation. We get 2 amps. In practice, switch current must be rated at least 30% more than this value. This leads to 2.6 amps. Let us now look at the conduction loss of the switch. We have seen in our previous videos that average switch power loss is given as shown here. Here, we consider maximum duty cycle. We know all the values except RDS on. On substituting them, we get RDS on into 6. The RDS on must be identified from the MOSFET datasheet. From our previous videos, we have seen that current I1 and I2 is represented in terms of average inductor and ripple current. Let us substitute all the known values to get I1 as 2.55 amps and I2 as 3.45 amps. From our previous equations, we know that switching loss is equal to Vout plus Vf into I1Tf plus I2Tr divided by 3T. From the above equation, we can see maximum loss happens when I1 and I2 are maximum. We can substitute all the known values in this equation. The rise and fall time can be found from switch datasheet or it can be measured on actual hardware. Let us now design the diode. We know that diode voltage is equal to output voltage when switch is turned on. Therefore, diode voltage is 15 volt. However, in practice, diode must be rated at least 30% more than this voltage. This will be around 20 volt. Average diode current is given as 1 minus T into inductor average current. However, we observe that with 2 duty cycles, we obtain 2 average current at minimum and maximum input voltage as shown. We can now substitute this value in average current diode equation to obtain diode current values. Thus, we get two current values, one at lower input voltage and other at higher input voltage. Here we can see that average diode current remains same irrespective of input voltage. In practice, diode current must be rated at least 30% more than this value. This is around 1.3 amps. Let us now look at conduction loss of the diode. Conduction loss is given as shown in the equation here. Let us consider minimum D at maximum input voltage to get the corresponding diode current. We get diode conduction loss as 0.7 into 1 minus 0.2 into 1.25 amps. This gives us 0.7 watt. In conclusion, we can see that the values calculated are for continuous conduction mode of operation. All values need to be validated in actual hardware. Some changes in values may be required based on actual measurement in hardware. All loss calculation values need to be validated in actual hardware. In this video, we saw an example to design boost regulator in continuous conduction mode of operation. We will learn more in our subsequent videos. Until then, let's keep exploring and learning. Thank you.